Observers, welcome to class. You may have noticed that we are not in class here, right? You pick that up. I'm recording this in January of 2022. We are in week 2 of the spring 22 semester at Antelope Valley College, and of course we had a lovely first week of the semester where, roughly a third of all my students were already out with COVID anyway. And at a certain point, the administration finally realized, hey, maybe this is pretty dumb. And so they're making us remote for, as of now, for a week, right? At least 1 week, which is pretty much what they said 2 years ago when we first started all this COVID nonsense. It was we are going to be remote for like a week, and it tied in like spring break or whatever. And, here we are again. So, yeah, that's the situation. I thought I would address that at the beginning rather than try to make this some kind of timeless video that I could just recycle for my students until I retire ultimately down the road. I thought I'd give you some context as to, why. Well, while you're watching this, you might be aware of that, but you also get a sense of where my head's at as I'm doing this recording. All right? And so, with the remote learning thing, we're still holding class, and technically, we're supposed to still be meeting at the class time, but what I've found with this whole pandemic remote learning stuff is that just doesn't work for people. It gets weird and complicated because of family things, job things, and all of that, as well as technical issues. So instead of holding some live Zoom, where I basically talk to a bunch of little black squares with your name on it, it's Zoom. Instead, what I'm doing is I'm just recording this. I'm talking to myself alone in my office. But putting this up so that you can watch it, listen to it, view it, whenever, right? So if you are dealing with, I don't know what elementary schools are doing and all that, but if you have kids who are suddenly home or they have to do Zoom or whatever, you're good. You don't have to be paying attention to a live Zoom thing while you're juggling other stuff. You dig? So that's the goal there. Also, you've probably noticed by now, and sorry, I don't know if this is working or not. I'm trying not to look at them, but I've got the subtitles going from PowerPoint. So it's transcribing what it is I'm saying, putting it on the screen. It's probably not great. It might be a little distracting. I know I always get sucked into it when I, hear what the person says and I go, it's not what the person says and all that. But I'm doing this to try to make it a little more accessible, at least in a way where I can actually get this stuff out without having to write down everything I just got done saying. All right, so contact me if you have any issues with the subtitles or any other accessibility issues. I want all of my students to have access to this material, but that's just more business to get out of the way early on. All right. So the plan here, and the goal, this is if we are actually meeting in class, the whole plan here is to talk about science. I spoke prior, the last lecture you had for me was on geography and what geography is, what geographers do, and we covered all of that stuff. And in that same vein, I want to make sure that you understand what science is, what scientists do. I want to make sure we're coming from the same starting point, right, for everything else that we deal with. All right, so we're going to get into science, what that actually means. We'll talk about the scientific method. And look, I get it. You guys have dealt with this for years now, I'm sure, having to, define science and work through the steps of the scientific method and blah, 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 blah. I get it. But the other thing is we're going to get into this in a more realistic way. Not just in a make the curriculum people happy when you're in third grade or whatever. We're going to get into what actual people who do actual science do. We'll talk about the scientific method and what it really is, not just in the abstract sense of step one, step two, and all that stuff, but we'll get into how this stuff actually, moves forward, how new scientific information gets out there and people get access to it and all that. And I'm going to connect it to COVID. Sorry, we're going to talk about COVID and mainly vaccines. We're going to get into this whole, this is just an amazing moment in time where we think, my hypothesis here, which I think is a pretty solid one, we'll also get into what that term means because we're getting all sciencey, but it dates back to the 90s. That's why the vaccine thing is just a complete disaster, and so I'll get into that and why some people are terrified of the vaccines and why we've never seen that before in human history and blah, 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 blah. All right? So we'll get into that. And then finally, we'll talk about the field sciences. Because that's another thing that drives me crazy, is that with this whole idea of science and the scientific method, if you do a Google image search for scientist or whatever, you have a person in a lab coat, in some kind of room, some laboratory thing, holding a beaker or a clipboard or something like that. Yeah, some people do that kind of science, and good for them. We need those people, but that's not what geographers do. We do science out in the field, and that can take many forms, and I'll get into that. But the things we study quite often are outside, and so we head outside into the world, the natural world, urban society, whatever it might be. We head out and we do our scientific, methodical research. So I'll get into that. Make sure you're all aware of how that operates. All right. So, our definition here. Science. It's the systematic study of the world around us. And if we were in class, I would ask you, students, what's the key word in that definition right there, that first line? And we'd have a variety of things shouted out. Study, world might be, tossed out by students, but the key thing, hopefully you already, this clicked in your brain when you first heard this, and if not, who cares? That's why we're here. We're learning, right? The key word, systematic. Right? That's science right there. Meaning, we have a system. We have a method. We have this process that we are following. We're not just going out, like whatever it is, we're studying. All right? We don't just kind of go, this is weird, and we just start, asking some questions, taking some pictures, thinking, whatever, and hoping for the best. Right? We don't do that. No, we do step one, we're going to do this. And step two, we'll do that. And we're documenting all of this as we're going through. And this ties in with the scientific method. Not the only way to do methodical scientific research and all that, but that's primarily what we're going to focus on here, right? We're following this method. So that's huge. Okay? Then two more terms here that are huge. We have verifiable. And I would say, what does that mean? And somebody would say, hey, you can verify it. And I would say, yeah, but what does that mean? All right, playing dumb, and everybody would get kind of pissed with me. This is what I love to do with students, and I hated it when teachers did it with me, but, it's a circle of life kind of stuff. But it's, if you're too vague, if you're not fully describing something, I'm going to ask you to describe it again. What do you mean you can verify it? And what we're looking for here is that someone outside of the people who did the actual scientific research can look at what was done and say, oh yeah, that makes sense. I see what you did here. That kind of stuff. You follow? And so this is why it's important to be so systematic in our approach and to also document this stuff, write it down. It's so that others can see what we did and realize we didn't get, just kind of sit out there and do whatever. We followed the proper steps. It makes sense, right? How we got to our conclusions. That's the idea with verifiable, right? Someone can check out someone else's work. And then repeatable, that term, is that we need to be able to repeat this system, right? The steps that we followed and get the same results, right? Ideally, someone else, some outside scientist or group of scientists or researcher or whatever, would be able to take what we did, perform all of the same experiments or grab the same samples, conduct the same statistical research, whatever has been done. They would do that and they would get the exact same result, proving that it was not some fluke, it was not a lucky guess or whatever, that there's some other outside factor we didn't take into account, but proving that that initial study is in fact correct. All right, that's the goal. And with all of this stuff, this is the ideal. All right, this is what we're shooting for. It doesn't always work this way. In reality, we'll see some examples of this or areas where, this is a place of problems within science and scientific research, but this is in its purest form. This is the goal. All right? So that's our basic definition. But now, let me give you an example of how this doesn't always quite work out. All right? And this, I'll go kind of quick. This is more fun to do when there are actual students in a classroom, because I try to scare the hell out of you. That's the main goal always. If you haven't picked that up yet, you will. Love to terrify my students with how things are going to kill you and all that. And so one thing I do is I talk about the pH of your drinking water. Do you pay attention to that? Are you aware of that? Did you drink water without knowing its pH today? My God, reckless, incredibly reckless. Yeah, you got to know pH. And do you know what pH is? It's a scale, right? And it's a way of looking at some kind of substance. So in this case, water. What we're testing here is how acidic it is, or alkaline, right? Or we call it a base as well. So it's on the opposite side of the spectrum here. Or in the middle of the scale, it would be neutral, neither acidic or alkaline. Okay? Acid, we can all kind of get a sense of what that is. Alkaline might be kind of, vague for you. We can say it's the opposite of acidic, but what does that mean? What we'll see in this class, we'll come back to pH from time to time, and it's an important factor in physical geography, but we tend to see it in desert soils. Soils that have a lot less water and vegetation running through, a lot more salt content. They're saltier soils. So desert soils are heavily alkaline, as opposed to in other parts of the world where you have a more humid environment, you'll get more acidic soils. But it runs from effectively 1 to 14. 7 in the middle is neutral. So anything less than 7 is acidic. Anything greater than 7 is alkaline. And so what we're seeing here are all of these common water brands. You can go to the store, buy some bottled water, but obviously not all water is equal. All right, we have different levels of pH. Propel 0 on the highly acidic side, a 3.5. Reckless. And of course, as this advertisement shows, there's only one pH of 10 in our drinking water, and that is Alkalife. Doesn't that sound, it just has life and alkaline in there. That's clearly that's what we want, right? They don't get into why at all. This is one fascinating thing about this stuff, and you see this in advertisements all the time. They'll invoke sciencey stuff. pH, that's sciencey as hell, right? Look at it. We don't even know what it stands for or whatever. At least I don't. I knew this before. I don't keep this in my head. I don't care. I just know it's sciencey. Sciencey as hell. All right, little p, big H. I mean, that's some science right there. And I don't really even know what this means, to be honest. Like why you'd want to attend, but my God, clearly it's important because they're advertising it this way. So I'm gonna buy Alkalife. Look, here's the deal. As far as I can tell, the reason why this is, and I'm putting my little finger quotes up here, important when it comes to drinking water, it can be traced back to this social media viral kind of thing where a parent and a little kid did this science fair experiment at a school. Right? And I only know about this because I had a student years ago who showed it to me, and she was freaked out, about this and wanted to replicate it and so on. But what happened was the kid, and you got the feeling that mom or dad or whoever was really behind all of this, bought, like a dozen different brands of bottled water and then tested the pH using litmus paper or whatever. We have a lot of different ways we can, test pH. Litmus paper is a very easy one here, and this is something people do when, pool maintenance. If you have a swimming pool, you're supposed to keep track of the pH or whatever, so you don't burn your eyes or have algae growing or whatever, right? So a pretty easy thing to test. So they do this, and they're being very systematic with the whole process, and it's verifiable. You can see what they're doing. And so it was a science fair thing, but then it got translated into like a Facebook or whatever post, right, showing this stuff and documenting with pictures and text like what was going on. So they tested all of this stuff, right, and saw similar results where everything had radically different pH levels. So far, so good. I mean, nothing here is false in and of itself, and it's meeting our criteria of science and all that. But then here's where the big leap is, right? It's a case where the original parent and kid, this science fair experiment, the whole thing, and I don't even remember the exact leap and how it worked, but effectively what they did was they connected things with low pH to high levels of antioxidants or whatever, then that leads to cancer in bodies. So effectively, if you drink something like, my God, if you drink Propel Zero, instant cancer. That was the big thing. And this is why it went out to Facebook or whatever it was. It was to let people know that you are drinking liquid cancer if you are not paying attention to the pH of your water. Dun, dun, dun. And it clearly had freaked out the student of mine who brought this to my attention and all that. And yeah, it looked sciencey, but you need to pause and think for a moment, right? Just pause and think about this. Like, why am I saying this isn't science? And why am I mocking the fact that people are paying attention to the pH, at least in this way, of their drinking water? I mean, if you think about it, have you ever had anything with a low pH before, something acidic? Like, I don't know. I mean, my God, have you ever had orange juice? Yeah, I'm guessing, right? Did you immediately get cancer after you drank that? I'm guessing no. All right, we can do that. And then if you also think about it, if I'm consuming something, where is that going? And this is always fun to ask students. This is so difficult. Like if you drink something, where does it go? And students are, your mouth, like, pee pee, whatever. What I'm getting at is it goes into your stomach, right? Your tummy tum. And what's in there? Acid. Like super hardcore acid, right? That's breaking stuff down and doing all this work to make the food or drink or whatever into something that our bodies can actually use. So it doesn't quite, like, if we follow this line of logic, it doesn't quite work. It doesn't hold up to scrutiny. All right? But that said, it went around social media for a little while, and shortly after that started to see these things pop up. And so to be perfectly clear, and I haven't done more than pay attention to some grocery store shelves. I haven't fully researched this, but it seems to me that this stuff came up later. But it could also be that I was only paying attention to it. But this exists. Where there's a lot of this. The pH is advertised, and it's supposed to be some kind of healthier thing. As far as I can tell, that's all nonsense. And feel free if you know of why it's really important to have a pH of 10 in your drinking water, let me know. Pass it along. But from what I can tell, this is crap. But it's sciencey crap, right? It's supposed to make us feel good about the stuff we're spending a ridiculous amount of money to buy, right? And of course, if you're really concerned with, the alkaline nature of your water, just go to the ocean, right? Drink some seawater, and I'm sure you'll be healthy as can be. I should probably put a warning here. Don't drink seawater. That doesn't end well if you do that. But you can see my point here. All right, so there's a little real life explanation or example of how it's supposed to work, but how it's also misused so often. That's a problem. Now, one key thing when we're thinking about science, and this ties in with the waters. Like, it's all well and good to learn a definition of science, to go through the scientific method, which, don't worry, little geographers, we're getting to that. It's all well and good to do this. But science is more than just following like a recipe, right? Or this method. We also need to think about, the whole thing, it's a way of thinking, right? It's a way of asking questions and answering questions and solving problems. And I'll say solving problems a lot in this class. It's something I do. But clarification here. When I say problem, like, it doesn't mean like a negative thing necessarily. It's more like, like how we use it in math class or whatever. It's a mystery. It's something we're faced with that we don't fully understand or we don't have an answer for or whatever, right? That's what I mean by problems, and that's where science comes into play, right? Here's something I don't understand. I want to understand it. I'm going to use this systematic approach to get some answers, to at least get closer to understanding it, if not fully understanding what's going on. All right, but in doing this, in using science or some kind of systematic approach to solve questions, we have two ways in which we can approach this. All right, we have deductive and inductive reasoning. And I have on the screen in these slides these two definitions they're great. I didn't come up with these. This is something that's used all the time as a definition of these terms. And they're phenomenal definitions if you already know what the terms mean. Right? If you don't know what this means, if you're learning it for the first time and you read this, you're like, the hell does that mean? Right? So deductive, for example, it says working from the general to the specific. And then inductive would be working from the specific to the general. Again, brilliant. Absolutely what these are. Doesn't really help though, right? So I use an example for both of these to hopefully help it make a little more sense. All right, we'll talk deductive first. And typically what I do if we're in class is I have you students imagine that we come into the classroom and a crime has been committed, right? Let's say there's a dead body in the middle of the classroom, just right there. And we go in there and we see this, and my God, we're going to solve this, right? What's our first step? And some students will always say when I bring this up, they'll be like, call the police. And I shut that down immediately for a variety of reasons. But number one, we don't rely on the police. We are people of science. We are brilliant, educated people. We don't need cops coming in to do this work. We're going to solve it ourselves, right? So no, we're not calling the cops. What are we going to do? And eventually somebody says, look for clues, right? And so yes, exactly. That's what we're going to do. To solve this, we need to find clues. And what kind of clues? And, people shout out the murder weapon. But the thing I always fixate on, because it's just kind of easy for this explanation, fingerprints. All right. DNA would also work, but we'll go with fingerprints because I like the old school nature of it. But fingerprints, we're going to dust for prints. We're going to try to find fingerprints in the area, and fingerprints that don't match the victim, don't match us, right, or people who have a reason to be in there, but we're going to look for some kind of odd fingerprints, because what's that going to tell us? That's going to be the murderer, right? Hopefully. We're talking simple here. Okay, so we know that we can take, we can go through the area, we can look for fingerprints, and that'll help us find the murder. And why is that, though? What the hell? How does that even work? All right, it's because one of you brave students will say fingerprints are unique, right? We all have our own patterns on our fingers, and we have things that are, we see connections and all that, but everybody's are unique. Okay? That is general knowledge. All right? We know this. We come into our problem already knowing this bit of information. All right? So we're using this general knowledge to figure out this specific problem. Right? The dead body, this is the problem that we're dealing with. So we're taking already known things, generally accepted and proven facts about how the world works, and we're using that to solve something specific. You dig? Hopefully that works. I have no idea because I'm recording this in the past. You're listening to it after I'm long done recording it, but and with all this stuff too, you can still ask me questions if you get stuck. I mean, the good news is you can rewind things or, whatever. But if you're still stuck with anything here and you feel like it's important or it's bugging you, shoot me an email. We'll talk, whatever. We'll get to it. But that's deductive reasoning. All right. Inductive, you can see, is working from the specific to the general. So if we stick with fingerprints, that fact that fingerprints are unique, well, that's knowledge, sure, but from where did that knowledge come? Right? This isn't something that we, found inscribed on some tablet somewhere, sent down from the heavens where it was, by the way, fingerprints are unique. No, this is something that humans had to figure out, right? And that's inductive reasoning. I'm looking at my fingers and I'm going, I got these little, curly lines on the end here. That's weird. And then I asked my buddy, hey, you got these curly lines? Hey, you do. But those look kind of different than mine, son of a gun. And I keep questioning and looking at it. And before long, I've realized that no one has the same fingerprints, right? I've taken this specific question or problem I've had, and I've turned it into general knowledge. This bold statement where I'm saying fingerprints are unique. And then the results of my inductive reasoning can be used for other people when they are doing deductive reasoning. Okay, hopefully that helps. Hopefully that makes sense. And so we'll use in this class plenty of examples of deductive stuff because we're not generating new knowledge in this 101 level class here. It's a survey course. I'm introducing a lot of stuff to new students. That's the way these first, second year courses you take are set up to be. All right, so we're not going to produce inductive knowledge. It's going to be in like problems I give you or when I pose you questions or whatever. It's going to be deductive based stuff. You're going to be using already known things to solve problems. But it's also important to understand this whole inductive idea, right? And that's the scientific method itself. Okay, that's what we're typically doing is we're following this method so that we can create general concepts, these big ideas that other people can use. And so everything we're going to get into when we're talking about climate change or plate tectonics or evolution or whatever it is in this class throughout the entire semester, what we're dealing with, look at that. I just glanced at the screen. Plate tectonics. I don't even know what that word means. Tectonics. Well, that's closer. All right, it's one word. Okay. Plate tectonics. No, it's beautiful. That's the word there. All right. Something. I don't even know what I was saying. I just got distracted. I think the point I was getting at is that all this stuff I introduced to you, I want it to be clear that this has been discovered, understood. This general knowledge has been produced through this inductive method, the scientific method. Right? And I'll give some very explicit examples of that down the road. But for now, we're going to talk about the method itself. Okay? So to do that, I have this. This was from some textbook we used ages ago. That goes through, and I just use it because, well, it works because it's a visual, and I also will tear it down because we tend to make this whole scientific method thing too convoluted, and we're stupid about it. So let's begin, shall we? So on the left, we have general process. So these are our steps of the scientific method. And then on the right, we have our example column. So it's trying to put it into a real world, example so that it makes it easier for you students to understand what's going on. All right, so general process, step 1, identify question. All right, right off the bat, that's terrible. Nobody talks like that. That's like robot speak right there. Identify question. No, the first step is to ask a question. Right? That's what we do. We don't identify questions. We ask questions. My God, I kind of get what they're going for, but I still think it's stupid as hell. I don't like it. But that's the whole idea. Science always begins. And honestly, this is inductive, deductive, whatever. This is research in general. So even, if you're in a major and you're going for a career where it's not science as defined by our rigid disciplines and all of that, you're here in college to learn how to, do something with these questions that we ask. We're always asking questions. That's weird. I wonder why this is the way it is. Or I wonder why this isn't doing what I want it to do. Or whatever it might be. What you're doing is you're beginning some kind of inductive problem solving. Right? We simply ask a question. And that's how I'll say this before we really get into the method, but as many of you are just starting out in college, that's how when you found the major that's for you, right? And that you should stick with college and go through it and all that. It's when you find yourself asking questions and you actually want to answer them in whatever, arena it is. For me, it was geography, right? That's the thing where I went, yeah, this is it. Because I do want to know what's going on here. And I was willing to put forth the effort to answer some of these questions, solve some problems and stuff like that. For you, it might have to do with something like, business or computer science or something in the medical field, nursing, something along those lines, right? Where you find that thing and you're like, yeah, that's cool. Yeah, I do want to know why this is the way it is and all that. When you get to that point, you're good. Right? And if you're not getting to that point, it is perfectly okay for you to kind of step back and say, what am I doing here? Is this for me? Right? Or figure out, like, how am I going to get to that point where I'm in these classes where I am asking questions and happy to, write papers or do projects or whatever because I like this stuff. All right? So just something to think about for you, scholars in training and all that. All right, that's pep talk over. All right, so step 1, we ask a question. And their example is, what is responsible for apparently stunted trees in a grove? What does that mean? It's asking about, we got tiny trees, right? Walking in some forest or some natural environment, and we stumble across some tiny trees. It's not the sexiest question we got. But you know, go figure. It's always, I love this because this is, was from an intro to geography textbook, and we in our different departments were always going like, man, why don't we have more kids signing up to be geography majors, right? And then in the intro examples we give them, it's like, hey, kids, do you want to go find out why we got tiny trees? Yeah, I mean, sure, you could solve disease or do other stuff, but we're getting to the bottom of the hard questions, like why are these trees so tiny? All right, so it's stupid, but like I don't have a better example. That goes through this, so I'll make fun of it, but I'm not helping the problem at all. All right, but let's just say, class, we're out hiking around, we're doing some field work, and we're seeing beautiful trees and landscapes, and it's gorgeous. And we get to this one area where we see the exact same trees we've been seeing, but my God, they are shorter. All right, and one of you says, hey, check out these short trees. All right, and I go, my goodness, you're correct. This is baffling. And we all together, we ask our question, why are these trees so tiny? All right, so that's step one. And because we are people of science, we're not going to just let it be there like, oh, that's weird, and move on. No, we're going to get to the bottom of it. Now, with this example here, and I know, like in the book that I have you guys read, the steps are different in there, and this is different, and they're all different. Don't freak out. I'm not ever going to ask you a test question like, what is number 3 from the scientific method exactly, or something like that. I just want you to have the general idea. You should know that our first step is to ask some kind of question here, right? But then from there, what they have here is gather information. And really, I mean, the best thing to do if we ask a question is we immediately, we Google that thing, right? Let's see if that answer exists. If you Google it and you immediately get this response that says like, here's why trees are tiny in groves, and it works perfectly for, this question we have, great, we're done. This problem has been solved. We don't need to move on. But let's say that gets us nowhere. This area hasn't really been heavily studied or researched. Like there's no answer already out there, right? Well then, okay, that's cool. And we're also gonna look around. We're gonna think about stuff, right? We're gonna ponder this question, and through this process, what we're trying to do is we're trying to create a hypothesis. And this is another issue where I have problems with this little diagram here, but it says form hypothesis and then generate predictions. Okay, and the main thing is, like I would ask in class, what's a hypothesis? And a handful of you would raise your hands and say, an educated guess. And why would you say that? Not because you know that's what it means, but because that's been beaten into you in your various STEM elementary schools or whatever. Right? That's the general kind of rote learning definition we get. Right? An educated guess. It's technically true, but I don't want students using that because we don't know what it means. It's just, again, it's been beaten into our heads. Right? But yes, a hypothesis, it's a guess in the sense that we don't have the answer yet. Right? All we can do is guess. And sure, it's educated in the sense that we're not just throwing out some ridiculous thing about, little tree gnomes decided to keep these short through bonsai techniques, or I don't know, something like that. That's silly because we have no evidence of the tree gnome bonsai people or whatever, right? We're going for something that is educated in the sense that it's founded in reality. Right? But also, and here's the key stuff with a hypothesis, and this is the main thing, it's something we can test, and in effect, a hypothesis is a prediction. Right? We are predicting the cause of this stuff, of what's happening. Right? So it all kind of works together. That's why this whole separating them into separate things, I don't dig. Your hypothesis, it's your prediction as to what the answer is. And it's testable in the sense that, if my hypothesis is tree gnome bonsai people, I can't test that. I mean, I guess I could. we could all camp out there and be watching for the little tree gnome people to come out and snip these things to keep them down, right? We could do that. I don't think it's going to be that productive, but it's something we should be able to test and actually figure out, right? We'll clearly be able to solve this one way or another. So the example for our sexy question is this sexy prediction. So it's saying the hypothesis low soil acidity won't allow nutrient uptake. Again, talking like robots. But this gets into pH. Okay? And so it's talking about the actual pH of the soil. And so it's effectively saying, look, we got tons of plant food, tons of nutrients out there for the trees. They should be big, gorgeous trees, like in every other place in this forest, right? But they're not, because the soil acidity, the pH, is different in this location, and that prevents the plant food from getting into the trees, and so they don't achieve their fullest potential. All right? That's the prediction. That's our assumption based on the information we have. We're being educated about it and all that. But what's great is we can test this. All right, so our next thing, we go past generate predictions, and it says design and perform experiment. Now the experiment thing, I hate that term because it conjures it again. It evokes this idea of people in a lab mixing fluids in beakers and all this stuff. That ain't geography, baby. That's not what we do. Some people do it. That's not what I like to do. That's not what gets people into geography. Instead of doing that kind of stuff, what we do, we don't so much experiment as we are sampling, we are mapping, we are measuring, and we're testing what we've found. Okay? And this goes back to the whole idea of spatial analysis, right? We're getting out there and we're seeing where stuff is, how that differs and how that influences stuff and so on. So what we could do to test this is we'll take soil samples in multiple sections of the forest, right? In our tiny tree grove, but also in other places where we have the same trees, but they're beautiful and tall and big and all of that, right? And we'll test the pH, and we'll test for different nutrients and see what's actually in the soil itself. And what's key is we'll map this out. So we'll connect it to the trees themselves, where we found it, differences in soil, and so on. We'll gather a lot of data, and as we're doing this, if it's not too big of a deal, we'll gather some extra data if it's feasible, just in case our prediction is incorrect, right? Maybe our hypothesis is off, but in doing this and actually mapping out this these soil samples and all that, we can compare it with other stuff down the road, because it's quite possible that what we find is, the hypothesis is not correct. Turns out that when we analyze this, no, actually there are places with tall trees that have the exact same pH, right? Or maybe we actually see differences in the level of nutrients, like the potassium or nitrogen or whatever it is way off in these different places, but in places where we've got tiny trees and big trees or whatever, right? So we might be wrong, and that's perfectly fine in science. Because hey, that's part of it, right? If you're always right, you're not asking the hard questions, right? You're playing it safe. That's garbage. We don't want to deal with that. No, you should be wrong. You should be asking questions and speculating and putting together these hypotheses and really reaching, for the big questions. And yeah, you're going to stumble. You're going to have things be incorrect, but you go back. Right, and so you see that little arrow coming back to in between hypothesis predictions right there. And the idea is, okay, that didn't work. Let's move forward. Let's try again. Let's think of what else could it be. And we'll analyze our data. Hopefully in what we're finding, it's triggering some kind of new hypothesis. Oh, of course it's not this, but let's test this. Let's see if this works. And we keep going until we get it right. All right, until we actually get to the bottom of our pressing question. Why them trees so tiny? Does that make sense? Hopefully that works. But here's the deal. A few different things here. This just kind of leaves it right here, right? Just like you keep going until you get it right, and then you all high five and you're good. No, got a few things, all right, that we're trying to do. Now, one thing worth mentioning here is this idea of scientific theories. This usually comes up when I'm talking to students in the classroom at some point. And in fact, when I ask for the definition of a hypothesis, people will say it's a theory, and that's not correct. Okay, a theory. Theory is a very important, precious word in science, in academia in general, research, just intellectual pursuits and all that. Theories are not guesses. They're not predictions. Okay, theories are explanations. We use this wrong all the time. This is one big problem, is that even people who should know better, they still use theory to mean, a guess, some kind of weak speculation or whatever. But no, theory, okay, in science specifically, but also when we're getting into, philosophy and other areas where we use this term, but we're going to focus on science here. A theory, it's an explanation that's rooted in so much work. All right? All sorts of scientific work, inductive work, deductive work, all sorts of things coming together, right, to craft this theory. One example I often use is Darwin's theory of natural selection. Okay? It's a case where this came into being over 150 years ago. It's a relatively old theory at this point in time. But what's great about it is that Darwin coming up with it, and Darwin wasn't even the only one to come up with it, as we'll probably talk about when we get to that point. There are others doing similar work at this time. But the theory itself, this is a result of Darwin sailing around the world and, having all sorts of observations and experiments and testing things and all that stuff. So it wasn't just some guess that this one dude had. But this, again, was over 150 years ago. And it's a case where people since the publication of his work have looked at this theory, questioned it, chipped away at it, or added to it, or whatever. It's been discussed and debated and challenged and all of that over and over. And we've had new scientific discoveries that have added to it. And we'll get into the details of this, but it's not some random guess. It's something that took a while to come into being and has since been worked on and refined and all that. And it's a great explanation for how a certain thing happens in nature, why it's happening, and all that stuff. Another thing that happens is people will say, look, if you scientists really believed in evolution, why don't you call it the law of natural selection or the law of evolution or whatever? And the proper response to that is, well, because that word means something different. Right? Laws are telling us what happens, right, under certain conditions out in nature. Right? A good example is if we're dealing with gravity. We all know the law of gravity, and we can demonstrate it. I can hold something up in my hand, and I can drop it, and it falls down. Cool. All right, but why? Why does it do that? That would be the theory of gravity, right? That getting into the why would be something totally different. So like the law of evolution would simply be, man, we got a lot of different birds, right? Man, look at all them different monkeys. Now, again, we'll get into this stuff, but it's the idea of why we have so many different species that are similar, but distinctly different to the point where they are separate species. So the law would just be, yep, got a lot of monkeys, but the theory of natural selection would explain how did we get all these different monkeys that we see today from some common ancestor and blah, 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 blah. That stuff we'll get into. All right, so that's a key thing. Just keep that in mind. Theories are wonderful, non-guessy explanations of stuff. Okay? But with this, when you're doing scientific work, like we're not, with this tiny tree thing, we're not trying to come up with the theory of tiny trees. Some masterful explanation that's going to be a universal thing, getting into the why and all that. Technically, yeah, but it's not when we're trying to get into the why of stuff. But it is still, theory is, I tend to reserve that for the bigger things that are out there. All right, but some of this stuff too, when we're doing work, we're not trying to come up with a totally new theory. Instead, quite often what we're doing is we're contributing to existing theories, or we're giving little pieces or more local examples or something. We're trying to find, examples of or exceptions to existing theories. That happens. Or we're just, all in all, we're trying to build on our scientific knowledge, our understanding of what's going on around the world. So quite often, the work we do as scientists or some other kind of academic researchers, we're not going to have these earth-shattering discoveries. We're just adding. We're contributing to some bigger thing. And in order to do this, this is where we get into the final step of the scientific method. And so if we go back to our example, it just ends with, make sure your hypothesis is cool and high five yourself. But no, the true final step of the scientific method, of just research in general, in the scientific sense, is to publish. You need to publish your findings, your results. You need to get it out there into the world in a very specific way. All right, so just I'm going to stress this. This is the final step. And effectively, if you don't do this, as far as we're concerned, in terms of science and knowledge and all of that, you haven't really done anything until you've published these results. Okay? That can be up for debate with others, but we're just going to keep it very black and white here in this discussion. Okay? And with publishing, this does not mean, like, it's not the parent and kid who did the little bottled water pH test and put it onto Facebook or whatever. Like, putting it on social media is not publishing. Right? Getting a website or something along those lines is not publishing in this sense. What you need to do is you need to get your work into a scientific or professional journal. On the screen, I've got some examples of these, different ones that would work for physical geography. And with this, these are all, you can think of them as kind of like magazines or some kind of periodical. They're not exciting. Like, I don't even know if you kids today even know what a magazine still is. But, this is very professional. It can be kind of stiff, not necessarily the most exciting thing to read. But these are all collections of scientific work, of studies that have been done, and they've undergone this specific process that we call peer review. I'm going to talk about what that is and get into how that works here. All right, but all of these here are peer-reviewed journals, and there are rankings and all sorts of stuff. I mean, there are a bunch of different journals. Some have a higher ranking, meaning that if you get your work in there, it's a little more impressive than others. And some of that can be nonsense, and that just gets into how we, in academia, kind of, advance our careers and stuff like that. Some of it's silly, but the general idea of just peer review, it's phenomenal. It's a fantastic thing, and it's something I want to get into. And if you've seen the movie on Netflix, Don't Look Up, which, if you haven't, it's worth taking a look at, my little geographers, because it's great in what we in geography have been dealing with for a while here. Some people hate the movie, some people love it and all that, but if, it's just a thing where like the idea of peer review comes up in there, and the idea of scientific expertise and all that, it gets kind of brought up and questioned and critiqued and all of this stuff. So that's one example. Maybe you've recently been exposed to this. But peer review, what it actually is where we do our work. Let's say we did our tiny tree work, right? We're out there studying this stuff, and we prove our hypothesis. We figure it out. Oh, it's this acidity, and that's what's going on. Blah, 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 blah. Well, our final step means we need to gather everything we did and type it up. We're writing a research paper. All right? And this is why you take English 101 or whatever it is, early on in college. It's a way to train you to be good little researchers and to be able to do this kind of stuff. All right, that's really what we're trying to do. So a research paper, it's not just some exercise we make you do. It's a way to get you to be able to contribute to the greater body of knowledge. So we would type up, we'd have our introduction like, hey, man, we found some tiny trees and we wanted to get to the bottom of it. And then we get into here are our steps, and here's what we did, and here's what we found. And that gets into the whole verifiable, repeatable thing, right? We're being very transparent and we're just saying, here you go. Here's what we've figured out. Check this out, scientific community. And so once we've got this paper together, we find the journal that we want to send it to. You just send it to one initially. You don't send it to a bunch of them. You pick one that you think is going to be a good fit. All right, the Journal of Tiny Trees, or whatever. The Journal of Tree Size, something along those lines. Oh, that'd be a perfect fit. All right, because they publish papers based on the kind of stuff we do. We wouldn't want to find some journal that's like the Journal of Places Without Trees, because that wouldn't make sense, right? These aren't journals, I don't think, that actually exist. But you get the idea, right? That's what we're finding a good fit. And so we send our paper to one of the editors of one of these journals, and the editor is going to look at it and they're going to say, okay, yeah, this seems like something that might be worth, moving forward with. Or they might look at it and say, like, no, this isn't what we're doing. Because they have limited publishing space and resources. It's a whole deal. So they might just say, like, look, thanks for this. Looks great and all that, but it's not what we're looking for right now, or it's not what we have space for. It's not exactly what the purpose of our journal is, or something along those lines. And then we start the process again, right? Until you find that editor that says, yeah, this looks good. We're going to move forward with peer review. Okay? And so the editor, will take our names off the thing and send it to, it can be anywhere from 1 to 4 different reviewers. It's just based on the journal itself and policies and disciplines and all that stuff. But they're going to send this anonymous paper out to some experts, some other geographers, some other people who have already published on trees or forest health or something like that. And so the question is, okay, why do they take our name off of it? And typically a student will say, bias. And I'll say, what does bias mean? And we'll kind of work through this idea. But it's the idea that we don't want our own personal reputations or any prejudices the other people have or whatever to influence the outcome one way or another. Quite often, it's adorable. I have students who say, like, well, if they send it to one of your friends and then the friends kind of just go like, oh, it's that guy. Yeah, this looks good. And they'll let it go through. Rarely does that happen. Quite often it's the opposite, is that we all hate each other. It's stupid, but this is how academia works. We're very petty, and it's mainly because we all think we're the smartest people in the world, and that other people are stupid. And so we have enemies. I have some professors that exist that I can't stand. So if I were to get one of their articles to review, there's a good chance that I would say, oh, it's that guy? I'm not even going to read it. I'm just going to reject it. Right? So in order to avoid that, hopefully by taking names off, it's just the science itself is what's being judged here, right? The validity of the work. We take all this personal petty nonsense out of it, and that's the goal. All right? And the other thing too is that these reviewers are anonymous, right, in this whole process. Something we often refer to as blind review. It's the idea that, they don't know who I am, I don't know who they are. And so that way everybody's free in terms of the reviewing. They can say whatever. And they don't have to worry that if somebody like rejects my paper, that I'm going to retaliate or go out and if they try to apply for a job at my college, that I'll block them because they were mean to me once or something like that, right? Again, humans are stupid, especially academics. And so we try to limit all of this stuff. Okay, that's the goal. All right, so these reviewers then, they read through the paper and they recommend, one of a handful of options. And I just try to do kind of a general thing here, but they can say, look, this is a good paper. This was some good science. Yes, let's publish it. Have at it, right? And that never happens, like just so you're aware. And mainly because even if we feel like this is a good paper, we don't trust that feeling, and there's always stuff that can be improved or whatever. So we rarely get that. What we're hoping for is, yes, we should publish this paper. We need some changes, right? And they can be minor, they can be pretty significant or whatever. But it's like, hey, tweak this a little bit. This isn't clear. You use this statistical test to prove this thing. Could you try it again with the same data but run this other test? Yeah, I think that would be valid, or something along those lines. So it can be pretty big, pretty minor, or whatever. But if you make those changes, yeah, the thing's going to get published, right? Or it's just a complete rejection. It's saying, look, this paper you did, it's terrible. It doesn't make any sense. You skipped all these steps. The links you're making don't track, like that kind of thing. Like, there's just so many problems with the paper. These experts are saying, no, this is not science. This is garbage, what you're turning in, right? That's a possibility. All right, and so these three, let's say it's three different reviewers are looking at your paper. They might have some different ideas there. Maybe one person says, rejected, it's garbage, but the other two say, no, this is good. It just needs a few changes here and there, right? The editor is going to say, okay, you know what? Yeah, we're going to go ahead and publish it, make these changes. And I've had editors where it has been like, yeah, look, we really need you to make these changes here. These are the key things. And then we're good, assuming the other reviewers go back and say, yeah, we're cool with this, right? So it's a whole process. But the idea is, what we're trying to do is to make sure that this isn't just one person speculating about stuff. This is a community, the scientific community coming together, discussing and debating ideas, so that by the end of this, any paper that's in a professional, peer-reviewed journal, it's going to have undergone this rigorous testing, and we can rest assured that the end result is good, right? That it's quality scientific work that's out there. That's why we care about peer-reviewed science. It's been checked, it's been tested, it's been verified. This is good stuff, right? That's the goal. And this is the best way we have to get new scientific work out there into the world. All right? It's also, it's brutal. It's awful. It's a terrible thing. I always dread it if I send something off for publication in this review process. There's always that like, why am I doing this to myself? Because it can be miserable. Number one, it can be slow. I mean, and that's even prior to COVID. I had stuff that took years for it to move through the process, and a lot of it has to do that with academics. We're volunteering to do this. We don't make money in reviewing stuff or even publishing, for that matter. No, big corporations make money off of us. We just kind of do it because we like to do it, and it helps us, maintain jobs, get tenure, that kind of stuff. So it's slow because it's this voluntary thing. It's also with COVID too. That's made it all super slow in many cases. But you can have things where just you're at the mercy of whoever these reviewers are. Sometimes you have people that are just jerks or difficult. Even with all these, steps in place, it can be so frustrating. That's what I mean by the different theoretical personal views and all that. I'm not going to dwell on them too much, but it's so difficult to get through this process just because you're dealing with humans. And it's in science and academia, it's always the term reviewer two is always, mentioned. It's kind of like a meme thing where it's just, things seem to be going good, and like reviewer two is just a jerk about stuff and is obnoxious. I've had some reviews where it's just like, I just want to start crying. They're so mean. And, but the editors will be like, look, okay, yeah, reviewer two, kind of a dick, but see what you can do with this. The rest of us think it's good. We'll try to move forward, right? There are ways forward with this, and it's the best way to ensure that good stuff gets out there. So we suck it up and we go through this miserable process. But here's it's not even the big problem, but here's a problem with this. Even though we have steps in peer review where we're trying to ensure that good stuff is getting out there, every now and then we have fraud that is committed. All right, somebody lies and submits something that is a lie. Sometimes this is done as a form of protest. We have things happen where people don't like the way a certain field is headed, and so they make up some study and they publish it, trying to get it published, and then after it's published, they say, we made it up, and they try to prove a point and get people fired and all of that. Sometimes that's a valid thing. Sometimes the people doing it are just obnoxious as hell. I mean, it's a whole deal. That's a separate thing. All right, but the really problematic stuff, because that immediately gets mentioned, and maybe some people quit or whatever, but it's not like, it doesn't destroy society, right? But then you have other things where people do just flat out lie, and in some cases it's a desperate effort to get tenure, keep a job at some prestigious school or whatever. So they're desperate, their research isn't going well, so they start making stuff up, right? And that can be a problem. There was some study years ago. It was like a guy lied. He was an anthropologist, and he lied about monkey facial expressions. I don't remember the full details, but it turned out it was found out after the thing had been published that he lied about, the faces that baboons made or something like that. Now look, the way baboons look at each other or the expressions they make, that's never affected my life, ever. So that's not a big deal, right? But then there are other studies where there have been people who lied and they have affected the world. And that's an issue. And this is a very minor thing. I mean, of all the studies that are published every year, this is a tiny fraction of a percent. This doesn't always happen, but when it does happen, it's bad and it's worth talking about. And the one that's really bad, that's really problematic, it has to do with vaccines. All right, and so there was a study back in the 90s, all right, and published in a very prestigious medical peer-reviewed journal. Okay, so stuff in this journal, and there are a handful of these prestigious medical journals where doctors are conducting clinical trials, scientific research, that kind of stuff, and testing this stuff out, evaluating hypotheses, all that, getting it through peer review, and that's how doctors continue to learn about diseases, right? And so we advance medicine and that kind of stuff. And so this article from the 90s is published, and it links autism with a specific vaccine, the MMR or whatever, the thing you get for measles and some other stuff. It links that, hey, kids who get this vaccine are more likely to become autistic in some way. All right, now that's major. All right, I mean, the whole vaccine thing is a major deal when you're dealing with your kids. I don't know how many of you out there have children of your own. I have a handful of them, and being a parent is both great and horrific at the same time. I mean, there are moments where the kids are just wonderful and adorable, and they're just little people, and you see like all the potential in them and what they're gonna do, and there's just so much love there. But then other times, and a lot of it's all connected to the fact that you're just terrified that something bad is going to happen to your children, right? And that's, I mean, COVID. My goodness, it's all like, if you're either afraid of them getting a disease and getting horribly sick and dying, or you're afraid of them being socially stunted because you're keeping them away from people and all that. I mean, it's just, it's exhausting to be a parent. So then if we find there's a study, there's even a possibility that me giving my child a vaccine is going to do something with their brains, right? And change them forever. And it should be clear that autism, it's not a death sentence. If you're autistic, it doesn't mean you can't function and all that. Although, it's the whole idea of the spectrum, right? I'm sure you've heard that term, where you can be, on one side of the spectrum where you're technically autistic, your brain works a little differently, but not that big a deal. You can go forth in life and function fine, and you're good. Be successful and find love and all this wonderful stuff. Or you're on the other side of the spectrum where just functioning with other humans doesn't work, right? And you've got issues that prevent you from having an independent life or something like that. And that's what parents freak out about. Just the idea that you might be harming your child, not letting them live up to their full potential, all because of a vaccine. And of course, if you don't get the vaccine, well, then we've got measles and we've got stuff like that. So you're weighing all this stuff, and it can just be frightening. Except here's the case. That study, it's all crap. It's completely crap. There is zero link between autism and vaccines. Zero. All right? Never been proven. And the thing is, the study itself, apparently, when it was published, it was even kind of published in it was kind of weak to begin with. Like the sample size was really low. There were some questions there, but it did get published. It got out there. And immediately, people are looking at this. They're questioning it. They're that's the whole verifiable, repeatable thing. Stuff can get published. That's going to trigger more discussion. People are going to start doing further research. No one was able to ever replicate this, but it was such a massive claim that it got to the point where journalists and people are investigating it, and it finally came to light that here's one huge thing. I mean, right off the bat, the fact that there was it was like 12 kids were studied, tiny sample size, and it was very questionable. I've heard a lot of stuff. I haven't fully documented. I need to go through and do this. Excuse me, because it is important. But I've heard all sorts of things, like the kids or the head researcher here, who did this, like his own kid developed autism and shortly around the time of the vaccine, and that's what got him thinking about it. And so he just studied his kid and his kid's friends in this tiny little group, and even there was a story about him paying other kids for blood. Like the whole thing was weird and creepy, and there were ethical issues there right off the bat. But then it got revealed that this researcher, his research itself was funded by lawyers who were trying to sue like pharmaceutical companies or something like that. There was a whole conflict of interest thing there that hadn't been disclosed at all. And so clearly, it's a case of not doing just pure, unbiased science, but trying to find a specific answer and cutting corners and doing sloppy work in order to do that. And the whole thing, the whole link, completely speculative, not a single bit of proof connecting these. That one big issue is just the fact that you had kids at a certain age, like at the exact same time when you typically get this vaccine, is the exact same time when we tend to see autism present itself, right? Just because these two things exist near one another, it doesn't mean one caused the other, right? That's pretty much science 101. I mean, and by this definition, you could also at the same time, it's when kids start losing their baby teeth. Right? How do we know that the baby teeth falling out doesn't lead to autism? And we should tape our teeth, keep them in your head for an extra few years to help prevent developing autism. It's the same logic there, right? Just because A and B are in proximity here, it doesn't mean A caused B or B caused A or any of that stuff. But that's what this study was getting at. So long story short, complete crap. There is zero evidence, and this has been tested repeatedly, that these vaccines will trigger some kind of autistic disorder in children. Zero. But here's the problem. It got out there. The idea spread, right, before it was fully debunked. And so this is in the brains of people. People who aren't medical doctors, who don't study this kind of stuff, have heard this. There's that concern, there's that doubt that's out there, and it doesn't help that we have some people who are out there spreading this, even though they should know better. They're just so convinced that there's a connection, and quite often you find it's because they have a kid, who developed autism, and they want answers, which is totally understandable, right? Um, but at the same time, like don't jump to these conclusions and don't, start just blaming everybody. And also, like, well, maybe we should, not make it seem like autism is such an awful thing too, right? And kind of focus more on like how do brains work and what's going on with these kids and how can we make their lives better and all of that. No, it's people screaming about vaccines. And so the problem is vaccines, they're actually really good. Go figure. And this is medical knowledge and technology that's been around for centuries. I mean, we had the founding fathers in the United States, getting vaccines and all that. This is not something new and scary. I mean, yeah, it'd be scary the first time where it's like, yeah, we're worried about this disease. Let me put a little bit of the disease in you, and I think you'll be okay, right? I mean, that first leap, scary. But the fact that they were doing that in the 18th century or whenever this stuff started, I mean, we can benefit from the fact that others maybe had some oopsies and all that. We've figured this out pretty good here. All right, but this has been an issue since the 90s and it's been growing. All right, it's been a thing where been this anti-vaccine movement, but it's rooted in a lie. And I think that's something that no one, like in the media and online, no one's very good about getting this out there. That this all starts, our America specifically, but also, Britain, Europe, pretty much the advanced, developed world, the wealthy people. That's how I'll put it. We see this distrust in vaccines starting in the 90s, starting with this fraudulent study, and it's just kind of snowballed to the point where now we're in the midst of a pandemic. And this whole idea of getting the COVID vaccine has become this issue, all right, where it never would have. If this pandemic happened in the 70s or the 80s, yeah, we'd all get the vaccine and we'd move on and be cool. Because that's just how it worked. I mean, sure, there'd be people who would trust it and some, but it wouldn't be like we see today. Like in the United States, where it seems to be this, down the line, people getting it, people not getting it, protesting about mandates and all this stuff. It's amazing where it's at. And what's so amazing is it's all rooted in lies. So keep that in mind. And I don't know, I just saw, and this is fascinating, there's a clip of Joe Rogan I saw online. I don't know if you guys have seen this or, listen to his podcast or whatever. But just a case where he's talking about, God, I don't even remember what thing it is, but the concern that you get the vaccine, like kids get the vaccine, and it screws up their heart or whatever. And there's this possibility of that. I don't know. My nurse wife would know the exact issue and what's going on. But Joe Rogan telling his guest, like, yeah, but the kids get the vaccine and they get this heart thing. And the guest says, well, actually, you're more likely to get it from COVID than if you than getting it from the vaccine. And Rogan says, no, I don't believe it. And the guy says, yeah, it is. And they wind up looking it up online and they find a study that proves exactly this. But Joe Rogan cannot, give in to this and say, I was wrong. How about that? No, he's committed to it. And that's not to pick on Joe Rogan himself, or like he would care if I pick on him. He's got $1 bazillion. He's doing fine. Or people who don't trust the vaccine or what. It's just saying, like, this is the problem. All right, we have these methods in place. We have the scientific method. This is what we have to advance society, to keep ourselves safe, to get new knowledge, to do all of these things. But our brains aren't scientific, right? We're rooted in emotion. We have this other stuff going on, and we get so invested in a side, vaccine's good, vaccine's bad, that when it comes to the actual science, we don't even pay attention to it, right? So I bring this up, and I go through this just to hopefully, hopefully let you know why people are afraid of vaccines. It's this fraudulent study, and you shouldn't be, right? And you can go out and look for information on this stuff. I mean, I've had students who tell me, yeah, I'm not getting the vaccine. I've done my own research. And I question that right there. Like, have you done your own research? What peer-reviewed papers have you looked at? What have you read through? What's the rationale? Because if you're doing your research with the people who actually study it, you're going to find right? The vaccine's okay to get. All right. And if any of you are, on the fence over this or just interested in it or whatever, and you're out there looking for information, always feel free. Email me a paper or some web link or whatever. If you can't figure out, is this peer reviewed? Is this good science? Unfortunately, too, we have people who work at universities who do terrible science, who somehow got a job and they still spread misinformation and it just causes trouble. So if you're out there looking for stuff, for information, and you're trying to do your research and you can't quite, make sense of it, or want somebody to let you know just some basics from the scientific standpoint, let me know. I'm not a medical doctor. I don't do, vaccine research, but I can at least say this is a reputable source. This isn't a reputable source, and I can help you guys figure that out. All right, that's the goal. That's the whole point of this real thing, is to make sure that you understand what science is, how it works, and how new scientific information gets out there. All right, hopefully that makes sense. And then also I have this slide in here about bias and the idea of being unbiased, and I would go into this in class if we had time. I have this question: should geography be unbiased? And it confuses students, mainly because it seems like, well, yeah, you don't want bias. Bias is bad. But my point with this, what I always work through with students here, is that yes, our scientific work absolutely should be unbiased. We should not let our own preconceived notions cloud our research design, the conclusions we draw, stuff like that, right? We don't want to do that. We want to have just as devoid of human emotion and prejudice kind of work as we possibly can, right? Which is not easy, being humans, but that's what we're going for. Okay, so good. We do that. We get this stuff out here. But one thing I love about geography, and this is what we geographers, this is what we do, at least the good ones, is we're biased as hell about how the world works. But that bias is rooted in unbiased work, if that makes sense. But we study stuff, like in this class, climate change. We're going to get into that. A lot of climate change work is done by geographers in the broad sense here. People who study climate and how it affects the world, doing spatial analysis in terms of the different climates we have and how this climate is changing and all of that. And it's been studied wonderfully unbiasedly. But look, we found that the climate is changing and that it's not good, that it sucks, that people are going to suffer and die. And quite often it's the people who are suffering from climate change are the poor people, right? Whether it's in this country or other countries. So the people who are already having a rough go of things, but climate change is going to make their lives much, much worse, right? So we realize, hey, something is bad. We're going to say that. We're going to let you know that this is bad. There was a real push. In fact, you go back 20, 30 years, there was a push by politicians to not have scientists, sharing their thoughts and views on stuff, that we should just shut up and do the work. And first, look at where that got us, right? World's on fire, flooding, all sorts of stuff. But it was also, I pushed back against this when I started teaching, and how stupid that is, that the people who actually know what's going on, who actually study this stuff, are absolutely the people who should have an opinion, who should be vocal, not the people, politicians or whomever, who just, say what is going to get them elected or whatever it might be, right? We should be listening to these researchers and geographers. Why I felt like these were my people. It's because they were the ones who said, yeah, this thing sucks. We got to fix it. And here's how we're going to fix it. Like actually moving forward with ideas. All right? That's what I mean by this whole bias and bias thing. We never want our work to be sloppy, but it's okay to have views about stuff, to work off the assumption that, you know what? A changing climate, a warming planet, all this stuff, yeah, that's bad. Right? That's bias in a certain sense. If I am coming across or approaching things with this idea, but we just want to make sure we don't let that screw up our work. All right, that's a little pep talk there. Finally, real quick, because I've been talking, I've run over. With these recorded lectures, I try to keep it within the time frame of a class period. I can see on my little clock on the computer, I've gone over a little bit, but hell, these YouTube things, excuse me, you can listen to them at 1.5 speed or whatever. 2, you can also pause it, come back. So I'm just gonna get this stuff done to get it done. All right. But the field science idea, I just want to make sure you're aware. This again is my little push, my effort to ensure that you realize you can get a job in something like geography, and it's a good job and a fun one and all of that. But to do science, it doesn't mean you're in a white lab coat, in some enclosed space, mixing fluids and beakers and, stuff like that. You can go out into the world. All right, this picture, I don't even know what the date is on this one. It was actually taken on film. It was a while ago. But this was some survey I did, just in this big expanse area. This is back in more the archaeology day stuff. But this is where the science was taking place. This is where the research was taking place, out in the world. This was a fun one, where it was a case where there were a bunch of unexploded military ordnance underneath our feet. We didn't exactly know where, but they, just the whole time, the military folks saying, just, be careful out there, because you might step on a bomb or whatever. That's fun. That's the good research. People just want you to be aware of that. Some of my latest field stuff from a handful of years ago, kind of pre-COVID now. But this was my laboratory. This was my research environment. It was out hanging out with rednecks and jeeps and, jeeping, driving over rocks. This is the road that we're on here. Kind of rough, kind of brutal, but a case where this was what I was interested in, looking at how people, in the four-wheeler lifestyle, how they connected with nature and viewed nature and the ways in which they tried to protect, conserve, and preserve natural spaces, and how that was at odds with ecologists and environmentalists and all that. And there was a lot of fighting, screaming, and personal battles. But when it comes down to it, there's this mutual investment in maintaining nature. All right, the guys in these Jeeps here in front of me, in front of the camera right here, they're not interested in, destroying nature and turning this into some, paved area or, killing all the trees or any of this stuff there. No, the whole point is to get out into nature, to have a natural experience, some wilderness experience, but doing so in a way that's different from how some other people view that. All right, and that was something I studied. And just so you know too, here's the great thing, is that I got money to go do this stuff. I mean, that's the other cool thing about doing this work, is that you can get paid to travel and explore and all of that. All right, something to think about. The other thing too, just so it's clear, because you might look at this stuff and I don't want to go outside, that looks awful. But some of my other work has been where I don't go outside, where I stay in and I do stuff. I did one paper on this green book, a thing for road trips for African Americans pre-civil rights era. So at the dawn of the motor age, it's starting in the 1930s. But when people are taking road trips, if they're white folks, they're cool. They can drive all over the country and have a great time. If you're black, no, there are some towns you don't want to go into, right? Some gas stations or restaurants or hotels you don't want to pull into, or entire towns or whatever, right? So this was a book that was published, and it was known within, African American circles. White folks seem to have not known about it at all. I mean, I certainly didn't know about it until one of these was presented to me in a museum, and I went, holy crap. First off, how did I never even think something like this would happen? Kind of showed how clueless we white folks can be. But it was also something I read through a bunch of these things and was analyzing them and looking at that stuff. But it was where I was, going through archival research, studying this stuff, and and trying not to be the white discoverer of something that other people already knew, but trying to, for white people especially, but just for everybody, kind of, pointing this out and thinking about what it means and so on, right? And then down on the right, Mad Max Fury Road, still right there. I have a paper on Mad Max and connecting it to climate change and just through watching movies, but also thinking about the science of stuff and the social stuff about things. That's another thing that you're able to do. That's what's great about geography and doing it in this kind of way, is that we can study anything. And there are different approaches we can use. And it can be traditional out in the field kind of stuff, studying tiny trees or whatever. Or it can be more, speculative things, or looking at different archives, different bits of evidence, and so on. But the key thing is it's all glorious. And it's a great field. And I'm once again encouraging you, think about it. Keep an open mind. This is a good place to be. All right. Okay, that does it for this this little YouTube video thing that you'll be watching, this lecture. Next time, I have planned geodesy. Look, I don't know if it's going to be me talking to you about geodesy in class. I don't know if it's going to be me, recording the rest of the semester this way. Who knows what the future holds here? So just, keep checking your email, Canvas, all of this stuff, and we'll get through it. We'll get through yet another ridiculous, crazy, god-awful, but hopefully productive semester. All right, geographers. Talk to you later.